All right, welcome. This is the AP Physics Workbook Solutions. Here we're covering Unit 3, Circular Motion and Gravitation. Here the section is 3.H, the rodeo ride. Here's the scenario. Carlos, which has mass M, enters the cardinal ride called the rotor. The ride begins to rotate, and once Carlos has reached a speed v, the floor drops and he does not slip. Many of you might not have seen this, and actually you don't see this anymore. The floor doesn't really drop. There are some rides like that. So let me show you a video that could give you a better understanding of it. Okay? So here are the students in the ride. They are starting to spin, right? They all have individual masses. Okay? Watch as it picks up speed. You see, you could still walk around, right? You're not fully pressed up against the wall. Okay? Watch as it starts to pick up speed. So think about this in terms of um, centripetal acceleration, okay, or the centripetal force. All right. Now watch as now they're all pushed up against the wall, and watch the floor drops. Do you see how the floor is going lower and lower and lower? But none of them slip down. Watch. They all stay where they originally are. They don't slip down, right? Watch as it slowly slows down, right? Watch as it goes faster and faster, right? At a certain point, you can actually not even move forward. You can't walk forward. It would be impossible, okay? You're going to feel so much force holding you back, all right? Watch, look. Right? They're not even falling any one bit, right? And it's only when they start slowing down, right? That you see now they're barely starting to move, right? You see now they can start going down. Okay, so this is what they mean by that. Okay, so you are going to draw a free body diagram to represent this scenario. That's what basically part A is asking for. Okay. Here I have some notes for you. If it's this is in an old textbook, and this is how it looks like. All right. So it depends on where the revolution is. Okay. So you need to understand that the radius is actually pointing outwards here. Okay. So there are three forces in actually this picture. One, the weight directly forward down, the frictional force directly upwards, right? And the normal force, which is directly towards the center of the circular motion. All right, and you're like, wait, isn't the normal force opposite to the weight in this case? All right, not when it's perpendicular like this, okay, or when it's in this scenario, okay? All right, so let's just label our forces. What was going down? It is the force of gravity. All right, exactly like what the problem said. Right, that is the weight directly downwards, the frictional force directly upwards, and that's going to be the same amount, force of friction, and the normal force directly inwards. So that is going to be the centripetal one. Right, the force normal is what's going to be causing a lot of their centripetal force here. All right, so there you go. All right, exactly like done, exactly like this. All right, okay. All right, so here, do you want us to derive some equations here for the normal force on Carlos after the floor has dropped? And okay, so they basically want Fn. All right, okay. So you can grab this equation here, right? But again, you can start wherever you want. Okay. So here, I will say that the force. You can start from the equation in your. I think you see this in your formula sheet. F is equal to m, multiply by m to both sides. You get AM is equal to the summation of the forces. Okay, I'm just going to rewrite this. All right. Do you see how I got this here? Okay, good. All right, I'm just going to make that the first step so people don't confuse how I'm getting this equation. All right. Okay, so what is the acceleration in the y here? The acceleration in the y that is getting caused, okay, in this case, the acceleration in the y is caused by the centripetal acceleration. Okay, so ay, so you're going to note, so here, I'm going to make the substitution that ay is equal to mv squared over r. All right, this is centripetal acceleration. So this becomes m v squared over r. And this, the centripetal force, is caused by the force normal here. All right. So you can write here for you the sum of all the forces the um, in the horizontal this should be x. All right. Yep. Okay. Exactly like the way this problem is done. Yeah. So it is fx is equal to mac. So it's fx. So the sum of all the forces in the horizontal direction is equal to Carlos's mass times the centripetal acceleration. Okay, is that how I spell it? Lera. Yep, centripetal acceleration. Okay, that's the first part. The second part is once you make that substitution, okay, notice that the only force that supplies that the only force that makes up the centripetal force in this situation is the normal force from the wall pushing Carlos towards the center of the circle. And you're like, what do you mean towards the center of the circle? Remember that the R is pointing away, okay? Is pointing away from it. So the centripetal acceleration is caused from the centripetal acceleration is caused against the wall. Okay. Normally, remember when we are in the other problems, your car is turning, right, and it's going towards the center. In this case, it's revolving, and you're getting actually pushed back. Okay. And so the centripetal acceleration is going up against the wall. All right. Okay. All right. So if you would like to see the deviation, okay, it's right here. Here's the problem. If you want to pause it and get down the deviation, go ahead. You can stop here. You could basically stop here if you would like. Okay. This is actually good right here. Right? In this problem, all they decided to do is actually find the period because you would an old problem is actually finding the maximum rotational period, right? How fast does the ride have to spin so that you don't slip off, basically, right? And this is one way of calculating it, all right? Okay. All right, so we're good there. Let's grab the data analysis and bring it up a little bit. All right. So on the next ride, he brings a force sensor and calculates this. All right. Okay. All right. Now it asks. Okay. Um, Which quality should be graphed yielding a straight line whose slope could be used to determine the radius of the ride? Justified your answer. Well, okay. So the input in this case would be the normal force or the speed, right? So what depends on what? Does the speed depend on anything or does the force depend on something, right? So the force, so I would say force depends on the speed, right? So this would be the force here, would be the output, which is the y value, right? Which is the y value. Good. And the speed is what you control. So this is what you control, which is your independent, which is the independent, all right, from algebra or integrated one. So this is going to be your input, which is called your x value. All right. All right. So let's graph this and let's see if it makes sense. All right. I decided to grab Excel. Okay. So here you have the input, which is the speed of ride. Boom. All right. Here, let me zoom in a little bit better for you. 5, 8, 10, 12, 15, and here you could saw this is the force that they feel up against the wall, right? Force from the wall. All right. 190, 540, 840, 1225, and 1850. I'm going to make this larger. Select all, right? Select the whole thing. Insert, scatter plot, the first one. That's how it would look like. All right. This does not look linear. I'm just gonna tell you now. This here looks very parabola in shape. All right. It looks linear. Trust me, it's not. Watch. If I add the trend line, you see? Doesn't behave that way. All right. So don't force it. Okay. So there should be no line. All right. So horrible. All right. So far, this doesn't work. All right. I'm just gonna be honest with you. This doesn't work. Okay. Here, you which quality should be graphed to yield a straight line? Justified your answer. You may use the remain column in the table above to record your qualities. Well, all I know is that this doesn't work. Okay. So we have to do a couple of things. All right. So it looks like it curves. So we have to get rid of that, right? In nature. So let's try to square something, okay? Um, you know what? Let's square this. All right. It's equal to, right, 190 squared. Oops, nope. Okay, whoa. Equal to 140 squared. I'm just going to square each term. And this, I'm going to make this 180 squared. Just look at how the equation is changing. All right. Is that helping? Uh, boom. And this is going to be equal to this squared. Boom. No, do you see? It looks more squared. So it seems like if you square the force, it becomes more parabola in nature. That's how you know it's not working. You want to linearize it. So not good. So we squared the wrong thing. All right. So we squared the wrong thing. How about we square this? So we're going to take the original and we're going to square it. All right, that became 25. Square this becomes what? 64 equals to 10 squared, 12 squared, boom, and 15 equals to 15 squared. Boom. All right. It looks a little bit more linear here. All right. Good. Okay. So this, let me just label the graph for you. This looks good so far. Let's just make that. So the input, right? The input. This is your input, right? The input was the speed of the ride squared. Okay? The output, nothing happened to it. This is still the force from the wall. And again, sorry, let me write the right units. That's it's newtons, and this is the speed here is still meters per second, right? But you're gonna square the whole thing, okay? Right? The speed of the ride squared, right? So click on it, right click, add trend line. So again, right click, add trend line. Okay, whoop. Add trend line. You could set you could display the equation here. There you go. All right. I'm going to use this. So this should fill. Let me just take a picture of this for you. All right. Okay. So let's go back here. So the right values here, if you want to change it right here, you can. I just grabbed this from my picture. Okay. So it's going to be the speed of the ride squared. Okay. It should be something like this. Boom. Okay. And the graph is going to be the next part. And the graph is useless here because I did it in here. So there you go. Boom. Okay. And again, please understand this was the speed of the ride squared. Alright. Good. Speed of the ride squared was here. Force of the wall is there. Force set linear using that. Now, using the slope calculate in part D, determine the radius. Determine the radius if Carlos's mass is 50 kilograms. All right, that's very straightforward. You could just grab any 2 points here. Did they say I can grab points off the line, or it has to be on the line? Use the slope. Calculate the slope. Okay, so I already have the slope. It's 8.29. Okay. Do you want me to really show you the calculation? Really? Okay. Let me grab 2 points here. How about I grab these two? Okay. Right. So if you want to see it, this is your x1, y1, x2, y2. Okay. Let's see. Let me calculate slope first, okay? So the m is equal to delta y over delta x, which is y2 minus y1 over x2 over divided by x1, right? Okay, x2, 540, subtract the 190, which is the change in the y. At the bottom, x2, 64 minus 25, right? And let's see if I can grab that in decimals. That's why I had decimals up, so here you go. Boom. Scientific. All right. 540, subtract 190. Divide the whole thing. Oh, that doesn't look pretty. So let me put the top in the parentheses. 540 minus 190. Close the parentheses. Divide this by 64 minus 25. Close it. Yeah, they got here they got 8.97. So here they got 8.97 roughly, right? It depends on what point you're selecting. Here, the calculator, they did the whole thing here, right? So this is the average, okay? It doesn't go up neatly. That's why the slopes are different. But you should get roughly around 8.9, 8.2, 8.5, right? Around those values, all right? Now you're going to determine his radius, okay? All right, so all you have to do to find the radius, okay, will be Carlos's mass divided by the radius of the ride. So let's take a look here. All right, where is that here? So velocity squared, right? That's the velocity squared divided by the r is going to be it. So we are going to have right here, the slope is 8.87, so we could say 8.97, okay, is going to be equal to Carlos's mass divided by his radius of the ride. So in this case, it's going to be Carlos's mass is 50, so 50 8.97 divided by r, okay, multiply by r times 997 equals 50, then divide by 8.97, divide by 8.97. Again, this is equivalent if you cross multiply, all right? R equals 2. Let me grab the calculator. Where's Desmos? Desmos, okay. Boom. So we have what? It was 50 divided by our answer. So it was 50 divided by our answer, right? Which was the 8.97. So, sorry, this was 50. Yep. All right. So it was 50 divided by our answer, which is our slope, which is the answer is 5.57. So it's roughly. So again, you can't do equal sign. You have to write it's because I approximate it. So it's roughly 5.7, right? Is that what Desmo said? Yeah, 5.57. 5.57, or if you want to round, this can be 6 meters, right? Just make sure you understand the units are correct here. Okay, meters. All right. Okay, so there you go. That is the radius of the ride to do this. All right. And here you go. I did this fairly quick. Just did it on Excel. Here's the data. Um, Here's the original equation. If you would like to see this, here you go. Okay. All right, there you go.